An explicitly defined curve is one that you're familiar with, right? Like if I say y equals x cubed minus x, we say this is explicitly defined just because y is all by itself on one side of the equation, everything else is on the other side of the equation, and there's no y's that appear on the right side. So we say that x is our independent variable, y is our dependent variable, and that's what we mean by explicitly defined. In contrast, you may or may not have seen this before, but a parametric curve is what I'm going to talk about today. A parametric curve is a function that has one input variable, and we're going to call t the parameter, and then it's going to have two output variables. So the coordinates x and y are going to depend on the parameter t. It's really easy to graph a parametric curve in Desmos. Some students think it's even pretty fun to do this. But in Desmos, if I wanted to graph a parametric curve, I'm going to have to open parentheses and then give some function of t, like, I don't know, call it cosine of t, and then type a comma, and then another function of t, like, I don't know, maybe t squared. And what I typically like to do to illustrate things is I make this little parameter t be greater than or equal to 0 and less than or equal to, I don't know, choose a symbol, right? Like it doesn't have to be capital T. But this way you can see what happens whenever you let your parameter go from 0 up to 10, right? It's tracing this curve as you increase the value of the parameter. It's telling you, for this value of my parameter, where do I end up? And if t is equal to 4, cosine of 4 is like negative a third, and 4 squared is 16, and that's how I get my x and my y coordinates along this path. And so choosing the right values of like sine and cosine can give you some pretty neat curves. Like this one, I think is kind of neat. And notice you couldn't ever get this from an explicitly defined curve where y is a function of x. For one thing, if you remember college algebra, this would fail your vertical line test because for one value of x, you've got two different values of y. So this is not an explicitly defined function, but you can still get cool stuff like this through parametric curves. And since sine and cosine are 2 pi periodic, you can trace out the whole curve from 0 to 2 pi. Okay, so one thing I could ask you is graph the following parametric curve by hand. And if I ask you to do this on a test, I'll tell you which values of the parameter I want you to use. Like this time I'm saying, let's like t go from 0 to 2 pi, and we're going to use a step size of pi over 6. So this is going to be a lot of values of t. And we're going to have to calculate the corresponding values of x and y. So t is going to go from 0 to pi over 6 to 2 pi over 6, and then 3 pi over 6, and then 4 pi over 6, and then 5 pi over 6, and then 6 pi over 6, and 7 pi over 6, and 8 pi over 6, and 9 pi over 6, ten pi over 6, 11 pi over 6, and 12 pi over 6 makes 2 pi, and so that's all the t values we need. That's what I mean by everything from 0 to 2 pi with step size pi over 6. And then if I want to calculate my x coordinate, I'm going to have to use cosine of t. Because this is my formula for the coordinate pairs x comma y. So what's cosine of 0?
1.
Yep. And you know, there's certain values where I just know, like cosine of pi is -1. Cosine of pi half is 0. Cosine of 3 pi over 2 is 0. And cosine of 2 pi, 1. Everything in between, you're allowed to use this TI-30X2S calculator on your test. And so for everything in between, like cosine of pi over 6, you can just type in cosine of pi over 6 and get 0.866. And like cosine of 11 pi over 6, well, I mean, I know that this is a periodic function. I know that it's kind of symmetric in certain ways, and so I can actually fill in these things without having to put it in my calculator more than once. Like this is going to be like this. Cosine of pi over 3 is 1/2. Okay. And then for the y coordinates, we have to do sine of 2t, not just sine of t. So what's sine of 0? 0. Then the next thing I really recognize is sine of, what's sine of pi? 0, yeah. All the integer multiples of pi are going to be 0. Then I need to put in my calculator sine of pi over 3, right? Because it's pi over 6 times 2. And get 0.866. And then sine of 2 pi over 3, I think, is also 0.866. And then sine of 4 pi over 3 should be the negative. So there's a little bit of annoying kind of calculator punching you got to do for this problem. Oops, those are positive. Positive, negative, positive, negative. Okay, but finally we've got this long list of coordinate pairs that are going to go in this order, and we can plot it. Like when x is 1 and y is 0, I can put a point here. When x is 0.866 and y is 0.866, it's going to be right here. When x is 0.5 and y is also 0.866, it'll be right here. And then x is 0, y is 0. X is -½, y is negative 0.866. X is negative 0.866, y is negative 0.866, and then x is -1, y is 0. And then negative 0.866, positive 0.866. I'm just plotting all of these coordinate pairs that we found in order. And then we're back to x equals 1, y is equal to 0. So if I were to trace this out in the order that we plotted these points, in the order that they appear, it's going to go like this. Oop. And this is not a perfect sketch, right? Because for one thing, I shouldn't have drawn it below -1. I know that sign has to be between -1 and +1, so that's obviously an error down here. But it's good enough, right? I'm not going to take off points if your sketch is a little bit rough. But you should be able to get the general idea, shape from it. Questions about this? All right, so as you're working your homework, I want you to use Desmos to check your work, right? Go back to Desmos and type in the parametric curve and think, does that look like what I just drew? Yeah, that's pretty good. So I must be no mistakes. If I got something that looked different, I would have to go back and find my mistake and correct it. All right. Exercise 2 says, eliminate the parameter to represent this curve explicitly with y as a function of x. So let's do that. This is called eliminating the parameter. And to eliminate the parameter, we say, well, it looks like y is equal to sine of 2t and x is equal to cosine of t. So I'm going to solve for t as a function of x. If x is equal to cosine of t, then t must be equal to arc cosine of x, because arc cosine is the inverse function of cosine. And now, you substitute that in right there, and we're going to end up with y equals sine of 2 times arc cosine of x. And this is explicit, where y is a function of x. You tell me the x, I tell you the y. There's no parameters anywhere, so we eliminated the parameter. Okay, question about that? Anything?
We don't have to solve for this, do we? We just have to write the equation.
Right, yeah, that's the solution, what I put in that box. Okay, so I put in parentheses, why would we want to avoid doing this? And I'll show you the answer here. Because if I were to type in y equals sine of 2 times arc cosine of x, I get this green curve. Are either of you colorblind? Okay, so you can tell the difference between the red and the green. So the problem is that the green curve really doesn't show you the entire story. The green curve that we found matches the parametric curve for part of it, but the restriction is this is a function, which means every value you plug in for x will only output one value for y. But the red curve we started off with is not a function. So you would end up getting 2 values of y for each value of x, or most values of x. And so whenever I write it like a function, it's going to lose part of the curve. Whenever I rewrite this as a function, it's going to naturally just get rid of part of the information. So if I asked you this question on a test, you could tell me something like, why would we want to avoid doing this? Because we lose part of the curve. And so that's the way that parametric curves are just a little bit cooler than explicitly defined curves, because you are allowed to do more stuff. You're able to do more curves with a parametric curve. Okay, exercise 4. Write the slope-intercept form equation for the tangent line at t equals pi over 6. So when t is equal to pi over 6, we get the coordinate pair cosine of pi over 6, which was like 0.866-ish, and then sine of pi over 3, which was also 0.866. And I'm actually looking for the tangent line here. Remember from Calculus 1, the way we found tangent lines. We started with the point-slope form of a line, and point-slope form says something like this. Where the point in my point-slope form is the x0, comma y0 point. And then since this is a tangent line, I want the m, the slope, to be the derivative of my function. So we're going to call this x0, we'll call this y0, and then I want this slope to be dy dx, because it's a tangent line. So if I were to take dy dt and divide that by dx dt, you could multiply the top and bottom by dt, since it's the same change in the same variable. Imagine multiplying the top and the bottom by dt, and it cancels out. That's the same thing as finding dy dx is finding dy dt, and then divide by dx dt. So dy dt is going to be the derivative of sine of 2t with respect to t. What's the derivative of sine of 2t? 2 cosine of what? Cal, what do you think?
Give me 1 second, I'm a little rusty.
Yeah, it was our first calculus question of the year.
So
You got to use the chain rule.
cosine 2t times 2?
Yeah, very good. So the derivative of sine of 2t is 2 cosine 2t, because of that chain rule. And then I'm going to divide by what? dx dt. What's the derivative of cosine of t? Negative sine of t. So that's going to be my slope. And specifically, I want the slope when t is equal to pi over 6. So that's 2 times cosine of 2 times pi over 6, or 2 times cosine of pi thirds, divided by negative sine of pi over 6, which is going to be 2 times, I think it's 1/2. I think it's 2 times 1/2, because cosine of pi over 3 is 1/2. Divided by negative 0.866. Is that right? No, that's wrong. I have a feeling that's wrong. Sine of pi over 6 is also 1/2. Sorry. So what is the slope here?
It'd be negative 1/2.
1/2. Try again.
Oh wait, shoot.
Yeah, the halves cancel, and you're left with negative 2. So whenever I use my point slope form of a line, I'm going to have y minus 0.866 equals negative 2 times x minus 0.866. And then I want this in slope-intercept form, which just means I have to distribute the negative 2, and I end up getting negative 2x. And then plus, because 2 negatives make a positive, plus 2 times 0.866 plus another 0.866 from the left side of the equation makes something like 2.598. That's what we're looking for. That is the slope-intercept form for the tangent line there. So I think most of this is pretty straightforward. Maybe the trickiest thing is whenever you get to the slope of your tangent line, you know it should be the change in y over the change in x. And since this is parametric, remember that you can do dy dt over dx dt to get that slope. All right, so if this is you and you're working on your homework, the way you would check your answer is you would go to Desmos and you would type in the parametric curve, and then you would also type in the line that we just found for our tangent line. We type in y equals negative 2x plus 2.598. And you'd say, yeah, does that look like a tangent line?
Yeah.
Is it tangent specifically at the point where t is pi over 6? Yeah, that's the point where t is equal to pi over 6. So that does the trick. All right. This says, write the slope-intercept form equations for the two tangent lines that appear at x equals 0. So there's not just one tangent line, because this isn't a function, this is a parametric curve. There's actually two different tangent lines here. Remember, this is giving me my x-coordinate, comma, my y-coordinate. So whenever I say that x is equal to 0, what we're saying is that cosine of t is equal to 0. What values of t make cosine of t equal to 0?
Pi over 2 and 3 pi over 2.
Mm-hmm. Okay, so there's two values of t that make x equal to 0. At t equals pi over 2, y is going to be equal to sine of 2 times pi over 2, which means y is equal to sine of pi, which means y is equal to 0. And then at t equals 3 pi over 2, y is equal to sine of 2 times 3 pi over 2, which means that y is equal to sine of 3 pi, which means y is equal to 0. Yeah, because sine of any integer multiple of pi is 0. So both of these tangent lines happen when x is 0 and y is 0. But we're still going to get two different tangent lines. To get the slope, we need the change in y over the change in x, which is going to be dy dt divided by dx dt. What's dy dt? We've already done this. We don't have to do it again. The derivative of sine of 2t was 2 cosine of 2t. And then we divide by negative sine of t. And at the point where t is equal to pi over 2, my slope would be 2 times cosine of pi. Cosine of pi is negative 1. So it's negative 2 divided by negative sine of pi over 2. Sine of pi over 2 is 1. So it's like negative 2 divided by negative 1. And the slope is 2. At the point where t is equal to 3 pi over 2, what's my slope going to be? Negative 2. Yeah, because the numerator stays the same, but when you go from pi over 2 to 3 pi over 2, the plus or minus sign on the sign switches from being positive value sign to a negative value of sign. So in the end, when all of the pluses and minuses are accounted for, I get a different slope. I get negative 2.
I have a question.
Uh-huh.
So why wouldn't it be undefined in the bottom then? Like, because I thought the sine of 3 pi over 2 was 0.
Sine of 3 pi over 2 is negative 1. Yeah, like on the unit circle, 3 pi over 2 is like 75% of a full rotation. You're pointing like the negative y-axis on the unit circle. So.
Okay. I think I just wrote something down wrong.
Yeah. Also, yeah, if this were a test, don't be afraid to check your work with your calculator. Even if you can do the unit circle in your head, that's good. But, you know, it doesn't hurt to just double check your answers with whatever resources you have. Okay, so finally I want to go and write my point slope form equation for the tangent line. Get something like that. We'll start off with at t equals pi over 2. We have x equals 0, we have y equals 0, and we have m equal to 2. So my equation becomes y equals 2x. At the other value of t, 3 pi over 2, x is equal to 0, y is equal to 0, m is equal to negative 2, and the tangent line is y equals negative 2x. All right. Good? Again, if you're doing your homework, I want you to check everything on Desmos, because using Desmos makes you smarter. Here we go. That's one of my tangent lines at the point where x is equal to 0. It's got a slope of negative 2. And then here's my other tangent line. If I set y equal to positive 2x, that's my other tangent line where x is equal to 0. Because that curve intersects itself right there. All right, so checks out. Exercise 3, rewrite the following explicitly defined curve as a parametric curve. This is a really, really easy question, by the way. I put this here on purpose because my Cal 3 students sometimes struggle with this, but it's easier than you think. If I want to rewrite this as a parametric curve, I'm going to say this is explicit for y, so we set x equal to t. Then y must be t cubed minus t, and the whole thing together would be t, comma, t cubed minus t. This is something that's kind of trivial, kind of easy, and it kind of doesn't really matter very much for Calculus 2. But in Calculus 3, this happens a lot, where you have to parameterize a explicitly given curve. And I wanted to introduce it this semester because it happens to be a stumbling block for Calculus 3 students. When you end up working on much more complicated questions, it's like, I cringe when I see students losing points over this. But anyways. All right, we still got 13 minutes, so we'll keep going. We'll do as much as we can from these notes. Graph the following parametric curve by hand. Use the values from -2 up to +2 with step size 1/2. So again, I'm going to make a table that has 3 columns for t, x, and y. Because here's my x comma y formulas. And I'm going to make t go from -2 up to +2 with step size 1/2. And x is just t squared. So -2 squared is 4. -1.5 squared is 2.25. -1 squared is 1. -1/2 squared is 1.25. 0 squared is 0. And then since x squared or t squared is an even function, I can just reverse it. For my y coordinates, I take the t value and I take t cubed minus t. So -2 cubed minus -2 is going to give me -6. I'm going to have to use my calculator for the next one. This will be -1.5 cube plus 1.5. And there's -1 plus 1 is 0. -1/2 cube plus 1/2 is 0.375. 0. And since this is an odd function, I should get the same values back, but with a minus sign in front. Or what I mean is flip the plus or minus sign. So now this is positive 1.875 and positive 6. There we go. All right, and so once I've finally created my whole table of values for my x and y coordinates for every value of t that I'm supposed to use, let's start by plotting 4, -6 here. And then 2.25, -1.875, and then 1, 0, 0.25, 0.375, 0, 0, 0.25, -375, 1, 0, 2.25, 1.875, 4, 6. Okay, so the curve is going to follow like this. I start down here, connect that dot, go to 1, 0, loop the loop, and go back through 1, 0, and then up. Again, let's check our work. And I want t to go from -2 to +2. So that's how it looks if I plot everything from -2 to 0. Here's how it looks if I go from -2 up to +2. I go woo, loop the loop, and then back up. Cool. And that looks like what we drew. So that looks nice.